Thank you. This talk is not on radio frequency. It's on how to correct flow calorimetry if you have a buoyant component. And what the title is, Buoyant Heat Transport Can Produce Unreliable Estimates of the Heat Generated in Flow Calorimetry absent OHMIC controls. And this is why it's important. We have discussed many problems with calorimetry, such as the things measured there, thermometry, electrical grounding, crosstalk, Nyquist issues, but the issues of buoyancy have rarely been discussed. And what I'm going to do in a very short talk here is to, one, prove to you the buoyancy effect is real, that it increases with heat. So if you're measuring excess heat, you're actually even going to get more of it. Grazie. I'm going to explain to you how to understand the buoyancy effect. We'll derive the Navier-Stokes equation by inspection when we get done, and then we'll show you that there is a non-dimensional number, A to buoyancy, A to B, which is the ratio of the heat that is transported by buoyancy instability over the total flow transport, and a simple correction would correct the indicated values to a semi-quantitative amount of excess heat. Now, I'm going to start where Jacques left off. Jacques pointed out on Tuesday that, in fact, you must have the temperature measurements in a flow calorimeter at the same height. If they're not at the same height, you get, if you have heat, you get rising of the flow. Flow calorimetry is not semi-quantitative, absent OHMIC control and buoyancy correction. And I'm going to show you how to correct it. Now, we first started talking about this in the 1990s. Some people didn't like the papers, so they removed them. That was the first one. But the fact is, the buoyancy effect is quite real. And it's something you know about. You see it in coffee. I guess you can't see it in cappuccino. But in American coffee, it's quite easy to see the flow. And this you're quite familiar with if you think about it. When you have a heated fluid, you're going to set up these vortices. And these occur at Rayleigh-Taylor wavelengths. They are called the BENARD instability, and we'll derive the whole thing. And from that, you get these processes where here you can see the flow coming up. Here you can see as a result of the heat, it's going to rise. So if you're measuring T1 and T2 and you're getting a flow up, a buoyancy, from the result of the heat, you're going to get an error in your measurement. I'll give you an example. When you go home, if any of you have an aquarium, measure the bottom and the top. There'll be about a half a degree, 3/4 of a degree difference. I assure you there's no excess heat in your aquarium. Here, for example, we can see as a result of that, these flow ups appear at relatively, well, these are Rayleigh-Taylor wavelengths when they come out equal, and we'll talk about that in a second. One other thing I pointed out at the CMNS site was that with increased temperatures, this gets even worse. So if you are measuring excess heat and you are having a heated, hot system, you really better do the correction. Here, what I was doing in this, we did an ultrasonic irradiation of our cell. This was way back in the 90s, where people were looking at cavitation, ultrasound on palladium, and we did the experiment. And you can see that there's a massive temperature rise as a result of irradiation, and it comes down over time. So the temperature differential in, let's say, a 1 foot high container can go from 3/4 of a degree, what you would see in your aquarium, even at rest, to here, it goes up to several degrees, and that will give an error signal. These have a time fall off of several minutes or more, and therefore they're a real part of what you have to correct if you do flow calorimetry. So I will show you how to write the Navier-Stokes equation by inspection. You just need two terms. We need the heat capacity and the heat flux, and you're all familiar with those. Specific heat times the mass gives you the amount of energy stored in a volume. And we know that with heat conduction, we put a surface integral on. We can look at the amount of heat that goes through. We do that in all our calculations when we calculate T1 minus T2, the outside ambient versus the core, and that gives us the heat flow. So here, for example, the heat loss that occurs through a volume goes as the surface integral and the gradient of the temperature, and it's actually quite easy to do. So let's derive the Navier-Stokes equation so we can do it. We start off with the conservation of mass. This is velocity. Del dot V is 0 in an incompressible fluid. The conservation of momentum, which is just F equals ma. And now we can write the Navier-Stokes equation as a conservation of energy on the back of an envelope, where we can see here, if we have a local volume, the rise in temperature of the volume, so it's specific heat times the mass, will bring this term over to this side, because that's the loss. And that's equal out the surface integral, that's this, is equal to the total amount of heat that's generated. Navier-Stokes equation, you can just write it down. And sometimes it's written as the convective derivative, and that's because you may have a moving fluid. So here we see rho dV dt, convective derivative. We have the forces here, and this term doesn't have the additional term of heat, which would be added right here. Now, here's where it comes from. It has to do with expansion of the fluid. When you heat a fluid, you're going to get thermal expansion, it's going to get lighter, and it's going to go up to the surface. And of course, that's why we have life on Earth. Because if we didn't have freezing from the lakes from the top down, we would have had it from the bottom up, and none of us would have been here. So we're quite lucky this happens. Finally, I don't know if you're familiar with the Buoyancy approximation, but when you write the Navier-Stokes equation, the only terms that really matter for thermal change of density is where it's multiplied by gravity. So the Buoyancy approximation is you skip it everywhere else except here. So that here is what we see. This is BENARD instability or BENARD-Rayleigh instability. And we can see it rise, and we can see it rise at the Rayleigh-Taylor wavelength. And we could spend more time talking about it, but I'd rather show you how to correct it so you can do semi-quantitatively correct flow calorimetry rather than just depend on the indicated values. All right, so we first wrote about this in the 90s, in this paper, 96. And what we found out, amazingly, because I didn't realize how important it was, is that with horizontal flow, we actually have the flow. A to B is a number that we use. It's a non-dimensional number that can evaluate how important this effect is. And what it is, it's the ratio of heat transported by buoyant forces that I've just shown you to the denominator of all applied solution convection. In flow calorimetry, it's the solution convection is what we assume only exists, but you have to add in the buoyancy term too. So if the ratio is greater than 0, it's important and it has to be corrected, and I'll show you how easy it is. Okay, A to B is also derivable from two other non-dimensional numbers, and you can find this on your own, the Archimedes number, which is that, and the Rayleigh non-dimensional number, which is that. And those two ratios also give you A to B. So here's the impact. And again, I apologize. When I sent the abstracts in, there were figures for all of these things, but they somehow got lost, and this is what it'll be. So what we're looking at here in this axis is increasing buoyant transport. So here's 0. So this direction is increasing excess heat. No excess heat here, a tiny amount here. Well, look what happens. If you start having buoyancy, you get a false signal. This is the indicated value of flow calorimetry that's not calibrated. Massive increase. Don't believe these numbers. I'll show you how to correct it, because what you want to do is go back to the equivalent to here. Okay, so from here, again, this just describes the graph. This is going from no excess heat to 300% excess heat, but the buoyancy can give you a real pseudo fake kilowatt. And I assure you, 3/4 of a watt of real excess power is a lot better than a kilowatt of made-up power, especially when the skeptics come and then correct it. All right, so let's jump ahead. This is the simple correction. And we can do this by considering the addition of the actual power out and an error term. This is what we got from the Navier-Stokes equation from the convection and the buoyancy. We do the correction, we throw in A to B, which is the ratio of the buoyant flow to the convective flow. We add the error term. Some of this has to do, it's second order, it really doesn't matter. And we end up with a single term, which is this. When we take the observed, the indicated excess power, and we subtract this, we get a corrected value. Therefore, these are, I deal not with COP, but we call it incremental power gain. So if you put in V times I, and you put in a watt, and you're getting out 2 watts, 1 watt is excess power, the gain is 2. We can correct the term of the power gain just by subtracting 1 minus A to B. All you have to do is multiply by the ratio. Into first order, you've done a correction. You've gone from the indicated value to a semi-quantitative correction, which now has value. Okay, let's summarize. Flow calorimetry is not semi-quantitative. You can sit there and calculate all you want, but the numbers are made up unless you correct for, that's if the input-output are at 2 heights. If they're at the same height, you don't have to worry about this. You can take the uncalibrated system with the correction and get an accurate semi-quantitative correction, and that would get rid of the false value. This is the term that's most important. You want to make the accurate measurement. You take your indicated value and multiply it by 1 minus A to B. And the reason I point this out is we've had enough trouble with skeptics attacking us over the last 30 years. Let's give them semi-quantitatively accurate data. And one other thing you want to do is use an OHMIC control right where your source is. I really recommend that when you do calorimetry, put an OHMIC control where the active element is. Put a square wave in. What could be easier than putting in a simple square wave? And if out of your calorimetry you don't get a square wave, don't trust your calorimeter. That's a test both for calibrating and to see if your calorimeter works. Thank you.
Thank you for this nice presentation. You saw my experimental scheme. Now, how can you comment the measure of the power coming from the heat? Because I have a sample holder and a small, let's say, piece of metal keeping in a low pressure system. What kind of error I can get?
I really don't understand your system totally, so
okay.
I can't go there. But if you do flow calorimetry at the same height at an OHMIC control, you'll get a semi-quantitatively correct value, no matter what the source of the heat is.